thank you for the introduction. And first of all, I would like to thank the organizer for giving me an invitation to talk in this great conference. Okay, thank you very much. So today, I want to talk about relationship between commutative algebra and graph coloring theory. So I think one of famous such relationship is cut algebra and four color theorem. But today, I want to talk about relationship between another algebraic object and some property of graph coloring theory. Okay. So if you want this slide, so you can download from this QR code. Okay. Okay, so, okay. Oh, wait. Okay, no. Okay. So first I want to explain some classical and important notation in graph coloring theory. So we say this notation is called Kempe switching. Do you know Kempe switching? No. Do you know four color theorem?
No.
No? Oh no. But so this Kempe switching first appears in the false proof of four color theorem. So what is Kempe switching? So this is a definition of Kempe switching. So I want to explain this definition by this illustration. Okay. So first we take one coloring. We start with these three colorings. Now we choose two colors. For example, red and green. And so we consider the induced subgraph on these two colors. Then, so this induced subgraph consists of two connected components. Okay. Then we choose one connected component. For example, we choose this one. Then we switch these two colors in this connected component, like this one. And so we back this new color to original coloring. Then we get another three coloring. So this process is called Kempe switching. Of course, if we choose another connected component, then we get another three colorings. Okay. So I also say the Kempe switching have been introduced by Kempe in the false proof of the four color theorem in 1879.
But it's the true proof of the five color theorem.
Yeah. So by using this switching, we can prove five color theorem. So unfortunately, his proof is false, but this operation is very powerful tool in graph coloring theory. So recently, the study this Kempe switching is the one of the main topic in graph coloring theory. Okay, this is example. So we say that two K colorings F and G can be equivalent if the coloring G can be obtained from F by repeatedly performing Kempe switchings. So of course, these two colorings are Kempe equivalent, and these two colors are also equivalent. And this one and this color are also Kempe equivalent. On the other hand, these two colors are not Kempe equivalent. Why? You can prove. So for this example, not difficult. Indeed, for any pair of colors, the induced subgraph on these two colors is always connected. This means all induced subgraph is always consists of one connected component. So this means the Kempe switching means just only switching in two colors in original graph. So this means the partitions associated to this coloring is not changed by Kempe switching. But so these two colors gives different vertex partitions. So this means so these three coloring are not Kempe equivalent. Okay. So we denote so CKG with a set of all K coloring of G, and so KCGK is the set of the closest set of so this can be equivalent. And so we say so each equivalent class is called Kempe class of G, and so capital KC so means the number of Kempe classes. For example, for this graph, the Kempe classes are only these two coloring. And so the number of such Kempe classes is just 2. But so in general, it is very hard to compute this one. But today, so I give algebraic methods to compute this one. Okay. So my first story. So first, we found a relationship between Kempe equivalence and an algebraic property. So this is the first main theorem. So we consider a simple graph G, and we consider the toric ideal of stable set polytope. So we define later. We will define later. This toric ideal is generated by quadratic binomials, if and only if all K coloring of any replication graph of G are Kempe equivalent. So namely, so we can characterize so quadratic of this toric ideal in terms of Kempe equivalence. This is our first main theorem. So by using this theorem, so we can give methods, algebraic methods to examine Kempe equivalence. Okay. This is the first story. The second story, if there is time. Maybe enough time. Okay, so we can generalize Kempe equivalence. So we say so R-colored switching and R-colored equivalent. So this is known. It was known that so all this is so the story of edge coloring. So all edge K coloring of a bipartite multigraph are always 3 colored equivalent. On the other hand, so this is a combinatorial result. This is algebraic result. The toric ideal of the full matching polytope of a bipartite graph is always generated by binomials of degree at most 3. Okay. So for full statement, so this result was shown for flow polytope. But so today, so we focus on only matching polytope of a bipartite graph. Okay. So our second main result is so these two different results are equivalent. Namely, so we can get this theorem from this one, and this theorem can be obtained from this one. So we found so this equivalence. Moreover, so finally, so I give a conjecture, following conjecture. So if so we restrict on the bipartite case, the toric ideal of matching polytope is generated by binomials of degree at most 3. If so we consider a general graph, then so we conjecture the toric ideal is generated by binomials of degree at most 4. So this is our main conjecture. Okay. This is the overview of my talk. Okay. So first I introduce the main algebraic object, stable set ideal. So the subset of the vertex set of graph is a stable set or an independent set if for each ij, so which is not in not h of g, then for any two vertices in S, so these two vertices does not form H. So for example, so the 1, 3 is not an H, so the set 1, 3 is stable set. On the other hand, so 2, 4, 5 is not stable because so 4, 5 is H. So this is the set of all stable set of this graph. So in particular, so empty set and each singleton are always stable. Okay. Okay, so now we define the stable set ring. So this is just a stable set. So this is just a toric ring associated to stable set. So namely, so the stable set ring is the polynomial ring generated by these monomials associated to each stable set. And so the stable set ideal is the kernel of this ring homomorphism. So namely, so the stable set Ig, this is a stable set ideal. Stable set ideal is a toric ideal of the stable set product of G. So where stable set product of is the convex hull of all indicator vectors of stable set of G. Okay. Okay. So next, I want to relationship between stable sets and K colorings. So given a K coloring F, so we can obtain several stable sets of G. In this, so each the set of vertices with the same color is a stable set of G. For example, we consider these three colorings. Then, so these red vertices and green vertices and blue vertices. So each vertex set are stable by definition. And so every stable set can be obtained from some K coloring. So from this corresponding, so we can get some monomial in RV like this. This is just, for example, so for these three colorings, so we get a monomial, which is a product of variables associated to each the set of the vertex set with each color. Okay. So however, so we cannot obtain every monomial in RG from K coloring of G. For example, this monomial cannot be obtained from K coloring of G. Why? Because so in this monomial, the vertex 1 appears twice. This means so that this vertex 1 must have two colors. So if so, we want to obtain every monomial by colorings, we should consider multi-coloring. So for this, so I want to define some graph, another graph. So for non-negative integer A, negative integer vector A of length D, D is a number of vertices. So we define graph GA as follows. So this is original graph G, and so we give the vector 2, 1, 2, 3. Then, so for each vertex, so we replace with a complete graph of AI vertices. Namely, so we replace this vertex 1 with this complete graph of 2 vertices. Similarly, so 2 replaced with this complete graph of one vertex, and 3 is replaced with this complete graph of 2 vertices, and 4 is replaced with this complete graph of 3 vertices. So 2, 1, 2, 3. And we join each complete graph according to original graph. Okay. So we call this graph GA is a GA replication graph of G. So now we consider a K coloring of this replication graph. This is just the multi-coloring of original graph. In fact, so we consider this replication graph G2111112. So the K coloring of this graph means the first vertex and sixth vertex has 2 colors. Okay. So we can describe multi-coloring by using replication graph. So by the same way, we can obtain monomials induced by this multi-coloring. Then we can get every monomial in RG from a K coloring of some replication graph of G. Okay. So by using this notion, we can give a system of generators of stable set ideal. In fact, the stable set ideal is generated by all binomials associated to 2 K coloring of some replication graph. Okay. And so by using this description, we can characterize when this ideal is generated by quadratic binomial. So I have already explained this theorem. So I explain again. So for graph G, the stable set ideal is generated by quadratic binomial if and only if for any vector A, all K coloring of replication graph GA are Kempe equivalent. Namely, capital KC GAK is always 1. So we didn't recall that these 3 coloring are not Kempe equivalent. This means the associated binomials of degree 3 cannot be divided by quadratic binomials in IG. So namely, this is a minimal generator. So IG is not quadratic. Okay. Okay. So next, I want to explain some application of this theorem. So why we consider this theorem? So because we want to attack some conjecture. So first we we define perfect as some more notation. So for a graph G, we denote the chromatic number by chi G and the clique number by omega G. So in general, clique number is always less than or equal to chromatic number. And so this is just not. This is just a small advancement for L-house theory people. So recently, I and Matsushita found the following theorem. So namely, the SG is a stable set polytope of G. the codegree is a minimal integer t such that the t's direct product of SG has an interior lattice point. So we know that the codegree plus 1 lies between these two invariants. So this is just advanced. This is not correspond. This is not related to coloring theory. So this is just so advanced statement for L-house theory people. Okay. Anyway, so a perfect graph is a graph G such that for any induced subgraph H of G such that so this equation holds. So on the other hand, so a perfectly contracted graph is a perfect graph with a nice property about Kempe equivalence. So today I don't give detailed definition, but because the definition of this graph is a little complicated. But so the following characterization conjecture is known for perfectly contracted graph. This is just conjecture. So the graph G, we assume that the graph G is a perfect. Then G is perfectly contractive if and only if G is odd hole, Anch hole, odd prism free. So odd hole is the induced odd cycle of length at least 5. And Anch hole, and hole is just a cycle, induced cycle of length at least 5. And Anch hole is the complement graph of hole. And odd prism consists of two triangles joining 3 paths. The lengths are odd. So we call this odd prism. So the minimal example of odd prism is this one. So we know this is not stable set ideal of this graph is not quadratic. So this conjecture says so this odd prism is not perfectly contracted. So from this conjecture, so we add algebraic condition to this conjecture. Namely, so assume that G is a perfect graph, then the following arguments are equivalent. So first is graph G is perfectly contracted. The second is G is odd hole, Anch hole, odd prism free. And stable set ideal is quadratic. So we recall our first quadratic result. So our ideal is generated by quadratic binomials if and only if this equation holds for any replication graph. On the other hand, so perfectly quadratic graph holds this property. Namely, so if G is a perfectly contracted, then this equation holds for 0-1 vector replication graph. So namely, so our conjecture means we can extend this property to all replication graph for perfectly contracted graph. Moreover, so by combining these two theorems, so we can show the ability to lead conjecture. Namely, so first this graph conjecture. If so this graph conjecture is true, then automatically so this our algebraic conjecture is also true. Okay, this one. So I think so. So these results give a good evidence for our conjecture. Moreover, so by using our result, we can show for several class, our conjecture is true, like these 5 classes. The last 2 graph classes were shown in the previous paper, Osugi, Shibata, and me. But so, our new proof are very simple than this original proof. Okay. So on the other hand, so for perfectly orderable graph, so we show that so the stable set ideal has square-free quadratic Grebner basis. This implies for this graph, the stable set ring is kosher. But so there exists a graph G such that stable set ideal is quadratic, but not kosher. But so on the other hand, so the perfectly orderable graph, almost all perfectly contracted graph are perfectly orderable, in my opinion. So we give the following conjecture. So if so, we assume graph G is a perfect graph, then these 4 conditions are equivalent. So, okay. Okay, next, so I want to give algebraic methods to examine Kempe equivalence. So first we consider the following quadratic binomials, binomial ideals. So first is the ideal generated by degree 2 part of stable set ideal. Namely, so generated by these binomials associated to 2 colorings of replication graph. Moreover, so we define JG by these binomials associated to 2 colors of GA with vector is 0, 1 vector. So this is just 2 colorings of an induced subgraph of G. So we call this second ideal the 2 coloring ideal of G. Then we know that the examining when 2 K colorings are Kempe equivalent is equivalent to ideal membership problem. Namely, so F and G are Kempe equivalent if and only if these associated binomials belong to these ideals. Okay. So for example, by using Macaulay 2, so we can check 2 K coloring are Kempe equivalent or not. So next, so we define more one ideal. So this is an ideal JG plus that is monomial ideal. So we can replace this JG with IG2. So we call KG the Kempe ideal of G. So by using this Kempe ideal, so we can compute KCGK, namely we can compute K Kempe class. So this is full statement, but so I think this example helps you to understand this theorem. So we consider this graph, then we compute standard monomials of this stable set ideal with some monomial order. Then there are 65 standard monomials of degree 3. In particular, standard monomials, these two standard monomials correspond to 3 colorings of G, these 3 colorings. So then, the above 2, 3 coloring form a complete representative system for KCG3. So by computing standard monomials, we can compute Kempe classes. So by using this theorem, so we can count K-Kempe classes by using Hilbert function. Indeed, so the Hilbert function of this link can be computed by the number of by using the number of K-Kempe classes for all in this subgraph. So on the other hand, so we can compute the number of K-Kempe classes of G can be computed by Hilbert functions of this link for any induced subgraph. Okay. Moreover, so it is known that this graph results. So let delta be the maximum degree of G. Then for any K, at least delta plus 1, then all K coloring of G are Kempe equivalent. Namely, so bracket capital KCGK equals 1 for any this K. So namely, so for sufficiently large K, so the Kempe classes consist of just one coloring. So by using this theorem, so we can know the Hilbert polynomial of this link. In fact, so the Hilbert function of this link coincides with the constant 2 to D. This is just constant for any this K. This implies the Hilbert polynomial of this link is 2 to D. Okay. So by using technique on granular basis, we can give several algebraic algorithms related to Kempe equivalence. Specifically, so our algorithm perform determination of Kempe equivalence and computation of a complete representative system for KCGK and enumeration of K coloring that are Kempe equivalent, and construction of a sequence of Kempe switchings between two Kempe equivalent K colorings. Okay. So this is the first story of my talk. So now, we turn to edge coloring. So edge coloring is a map from edge set to the integer 1 to k, such that for all h e1 to e2 with such that so these two have common vertex, then these colors are different. For example, this is 3 edge coloring. So this red edge, these two edges have common vertex, so these colors are different, must be different. Okay. So it is known that the HK coloring of G is just a vertex K coloring of a special graph. Namely, so the edge coloring is a special case of vertex coloring. So I explain this. So the line graph of G is a simple graph whose vertex set is the original edge set and whose edge set is this one. Namely, so two edge forms an edge in this graph if and only if these two edges has a common vertex. For example, so this orange circle are vertices in LG, and so these two vertices are adjacent because this edge and this edge have common vertex. Similarly, so 1, 2, 2, 4 has common vertex 2, so these two vertices has edge. But so 2, 4 and 1, 3 does not have edge because 2, 4 and 1, 3 does not have common vertex. Then the edge coloring of original graph corresponds to vertex coloring of line graph of G. And so stable set of line graph is just matchings of G. And the stable set ideal of line graph of G is just the toric ideal of the matching polygon of G. So their result is just if so graph G is a bipartite graph, then this stable set ideal is generated by binomials of degree at most 3. So in our quadratic results, so quadratic generator corresponds to Kempe equivalent. So then what does minimal generator of degree at least 3 corresponds? Something. What is this? So for this, so we introduce R-colored switching. So this is also the formal definition. But so I want to explain this definition by this illustration. So we consider this 4 colorings. And so now, so we choose 3 colors. For example, blue, red, green. And so we consider this in this subgraph on these 3 colors. And we take another 3 colorings on this graph. So you can choose 3 coloring which you like. Then also we back to this 3 coloring to original coloring. Then we can get new 4 coloring. Okay. So we call this process R-colored switching. So if we use R colors, and we say that so 2 K coloring F and G are colored equivalent if G can be obtained from F by repeatedly performing R-colored switching. The definition of Kempe equivalence and 2 colored equivalence are different, but the 2 K coloring are Kempe equivalent if and only if 2 K coloring are 2 colored equivalent. So this equivalence is the generalization of Kempe equivalence. So by using this notion, so we can characterize the maximal degree of minimal generators of stable set ideal. Namely, this is a general graph G. Then, so the stable set ideal is generated by binomials of degree at most R, if and only if all K coloring of replication graphs are R-colored equivalent. So we recall this result. So this is the line graph version of their result. So let G be a bipartite graph. Then the stable set ideal of this stable set, this line graph is generated by degree at most 3. And for the bipartite graph G, all vertex k coloring of line of a replication graph of line graph G are 3 colored equivalent. So by using this theorem, we know that these 2 theorems are equivalent. So these 2 results are for bipartite graph. First, our result is for arbitrary graph. So by using this result, we can consider non-bipartite case. Anyway, so we can classify bipartite graph G such that this stable set ideal is generated by quadratic binomials. So let's G be a bipartite graph. Then the following arguments are equivalent. So the stable set ideal is quadratic. So the line graph is perfectly contractile. And G has no odd subdivision of the complete 2, 3 bipartite complete graph as subgraphs. So this means the 4 line graph of bipartite graphs, so our conjecture is true. And so our Koshul conjecture implies this leads to this conjecture. So in above case, this case, so the stable set ideal has a square-free quadratic grammar basis. In particular, it is Koshul. So this is open. But I believe this is true. Okay. Anyway, so now we consider non-bipartite case. So we consider this graph. Then, these 4 colorings are not 3 colors equivalent. It is not easy to check these 2 colors are not 3 colors equivalent. But this is just fact. These 4 coloring are not 3 colors equivalent. This means the corresponding binomial is a minimal generator of degree 4 for that is stable set ideal. So this is my last slide. So from this computation and another graph theory conjecture, I give the following conjecture. So if G is an arbitrary graph, in particular non-bipartite graph, then the stable set ideal of line graph is generated by degree at most 4. So I remark that it is sufficient to show the case when G is a complete graph. And so we check this conjecture up to 7 vertices. I remember for 7 vertices case, so we compute the complete graph of 7 vertices. Then the stable set ideal has 200,000 generators. So I need 3 days for computing. I think so. For 8 vertices, I think it is impossible to compute. And so this conjecture, why so we consider this conjecture? Because this conjecture comes from some conjecture by astronomian. Okay, so namely, we show this, we can show this conjecture, we can get some graph theory result. And so this conjecture leads the following conjecture. So the theoretical ideal of the perfect matching polytoph is generated by quadratic of degree at most 4. Yeah, because so the perfect matching polytoph is a phase of matching polytoph. On the other hand, so namely, so this conjecture implies this conjecture. But so in general, so the other direction does not always hold. But we show that so these conjectures are equivalent. Namely, so it is sufficient to show so for this case. But so for this conjecture, I checked up to 8 vertices. But so 9, yeah, okay. Okay, that's all. Thank you for your attention.